Definition and purpose of Solidity. Solidity is a high-level, statically typed programming language designed for developing smart contracts that run on the Ethereum blockchain. Its purpose is to enable the implementation of smart contracts, which can be used for various decentralized applications, DApps, voting systems, financial exchanges, and much more. Solidity is similar to JavaScript and is aimed at providing a means to write clear and executable code for blockchain environments. It allows developers to define custom data types, control structures, and to securely handle transactions and interactions with blockchain state. No code is provided here, as this entry serves as an introductory definition. Smart contracts and blockchain basics. Smart contracts are self-executing contracts with the terms directly written into code. They run on a blockchain, which is a decentralized ledger that records transactions across many computers so that the record cannot be altered retroactively. Smart contracts can automate transactions and enforce agreements without the need for intermediaries. The given Solidity code defines a basic smart contract named Simple Storage that demonstrates how data can be stored and retrieved on the Ethereum blockchain. The set function allows users to store an unsigned integer, while the get function allows anyone to retrieve this value. This contract doesn't handle any ether and doesn't provide any access control, but it's a starting point for understanding how smart contracts can manipulate and store data. Ethereum Virtual Machine, EVM. The Ethereum Virtual Machine, EVM, is the runtime environment for smart contracts in Ethereum. It is a completely isolated environment, which means that code running inside the EVM has no access to network, file system, or other processes. Smart contracts are written in high-level languages, such as Solidity, and then compiled into bytecode, which the EVM can interpret and execute. Since EVM is not a tangible component that can be represented as a code snippet, we'll discuss its functionality. The EVM allows the deployment and execution of smart contracts, offering a layer of abstraction between the executing code and the executing machine. This abstraction ensures that the programming logic is insulated from external factors, providing security and predictability. All Ethereum nodes run the EVM as part of their blockchain operations, achieving consensus on the state and outcome of each transaction. A high-level overview of DApps, decentralized applications. Decentralized applications, DApps, are applications that run on a peer-to-peer network of computers rather than on a single computer. They interact with smart contracts, which are programs that run on blockchain platforms like Ethereum. Solidity is the programming language commonly used for writing smart contracts that power DApps. In essence, the DApp front-end communicates with the blockchain via smart contracts, ensuring transparency, security, and integrity of data without a central point of control. The provided Solidity code defines a simple smart contract called Simple Storage that could be part of a DApp. This contract has a single public state variable stored data to hold a numerical value. There are two functions. Set allows users to store a value, and get allows anyone to retrieve the stored value. Set alters the blockchain state, while get simply reads from it. This basic example demonstrates how a smart contract manages data that a DApp could interact with. Solidity versions and releases. Solidity is an evolving language with regular version updates that introduce new features and fix issues. Due to its maturity and frequent release cycle, it is important to specify the version of Solidity your code is intended for. This is done at the beginning of your Solidity source file with the pragma solidity directive, which tells the compiler which versions of Solidity the code is compatible with. The line of code, pragma solidity 0.8.0, indicates that the Solidity file should be compiled with a compiler version that is greater or equal to 0.8.0, but less than 0.9.0. The caret symbol is used to denote compatible releases according to semantic versioning. Using this pragma ensures that your code is not compiled with a version of the compiler that could introduce changes you aren't prepared for, such as new language features or altered behavior of existing ones. Development environments: Remix, Truffle, Hardhat. Remix is an open-source, web-based development environment ideal for beginners and great for quick prototyping of Ethereum smart contracts written in Solidity. The code is a basic smart contract in Solidity deployed on Remix. The pragma line specifies the compiler version. The contract named Hello World has a single public state variable greet, initialized with a string. Structure of a Solidity file. A Solidity file typically has a defined structure to make the code readable and enforce good practices. This includes the version pragma, imports, contracts, and their respective elements like state variables, functions, and modifiers. We will break down a simple example to illustrate these components. The provided code begins with a pragma directive, which specifies the compiler version for Solidity, ensuring compatibility and preventing compilation with older versions that may have different language features or bugs. Following that, a contract named Simple Storage is declared. Inside the contract, there is a uint56 state variable number that is publicly accessible. Two functions are defined: setNumber to assign a value to number, and getNumber to retrieve its value. The public keyword means these functions can be called from within and outside the contract, while view implies getNumber does not modify the contract state. Comments in Solidity. In Solidity, as in many other programming languages, comments are non-executable texts added to the code for the purpose of providing explanations and making the code more readable for humans. They are ignored by the Solidity compiler and do not affect the compiled smart contract's behavior or size. Solidity supports single-line and multi-line comments, similar to JavaScript. Single-line comments are initiated with double forward slashes, sla, and anything following them on that line is considered a comment. Multi-line comments start with a forward slash and an asterisk, and are closed with an asterisk and a forward slash, spanning over multiple lines. Solidity also introduces NatSpec comments, which begin with triple forward slashes, or a double asterisk block. These special comments are used to provide rich documentation that can be used by tools to generate human-readable documentation for smart contracts. Variables and types. In Solidity, variables are a means of storing data that can be used throughout your contracts. There are different types of variables to handle various kinds of data, such as integers, booleans, addresses, and more complex data structures like arrays and structs. Let's go over the basics of defining variables and their types. In the provided Solidity code, count is a state variable of type uint, unsigned integer, which means it can only represent non-negative integers. State variables are stored on the blockchain itself and are part of the contract state. The keyword public makes the variable readable from outside of the contract. The function increment_count demonstrates how to update the state of a variable by incrementing count by 1 each time the function is called. Value types, bool, int, uint, etc. In Solidity, the term value types refers to types that, when declared, allocate a fixed size of memory and operate on the actual value stored. Simple value types in Solidity include Boolean, integer, and fixed point numbers. These types are not references and are typically copied where they're used. Let's explore some common value types and their uses. The code declares a contract named ValueTypesExample, which showcases the use of common value types in Solidity. A Boolean variable isValueTrue is declared and initialized to false. The int type is used for the negative number variable, allowing both negative and positive numbers, and it is set to -100. The uint type, used for positive number, only allows positive values, including 0, and is initialized with 100. The value types here are direct and immutable, residing at the exact location where they are declared. Reference types: arrays, structs, mappings. An array is a collection of elements that are of the same type. In Solidity, there are two types of arrays: fixed-size arrays and dynamically sized arrays. Fixed-size arrays have a set number of elements which cannot change, while dynamically sized arrays can grow or shrink in size. The code defines a contract array example, which contains a fixed-size array fixed array with 5 unsigned integer elements and a dynamically sized array dynamic array. The function addElement allows you to add an element to the dynamic array, and the function getElement allows you to retrieve an element from dynamic array by its index. Visibility of functions and variables: public, private, internal, external. In Solidity, public visibility means the function or variable can be accessed both internally within the contract, and externally from other contracts and transactions. When a variable is set to public, Solidity automatically creates a getter function for it. The public number variable is declared with public visibility, allowing it to be readable from both inside and outside the contract. The setPublicNumber function is also public, enabling anyone to call it and set the public number variable. Control structures, if, else, while, for, etc. In Solidity, control structures are used to alter the flow of execution. The if, else, while, and for statements operate similarly to other programming languages, providing conditional execution and loops. In this code snippet, an if-else checks if value is greater than 50. If true, it halves the value, otherwise it doubles it. The for loop iterates 10 times, incrementing value by the loop index I each iteration. The while loop repeatedly increments value by 5 until value is no longer less than 100. Functions and function modifiers. In Solidity, functions are the executable units of code within a contract. They can read and modify the contract state and emit events. Functions can have various visibility specifiers like public, private, internal, and external. The code defines a public function add with 2 parameters a and b. The function is pure, meaning it doesn't alter or read the contract state. It returns an unsigned integer, which is the sum of a and b. Events. In Solidity, events are a way for contracts to communicate that something has happened on the blockchain. These can be listened to by the external clients, such as user interfaces, which can react to the events accordingly. In the example, we declare an event named newValue with parameters, the sender's address and a numerical value. This event is emitted in the triggerEvent function, which takes an unsigned integer as input. When this function is called, the newValue event is triggered, passing the caller's address and the input value as arguments. External listeners can then watch for newValue events and take action when they see them. Events are a vital part of creating decentralized applications, enabling real-time responses to blockchain activity. Error handling, assert, require, revert. The assert function is used in Solidity to test for internal errors and invariants. A failed assert indicates a bug in the code. It consumes all gas when a failure occurs. In this example, assert used to check that a condition value equals 100 holds true. If not, the transaction is reverted and all remaining gas is consumed, indicating an irrecoverable error. Global variables and functions. In Solidity, global variables and functions provide information about the blockchain and allow interaction with the contract itself. These are inherent features that are accessible without the need for explicit declaration or definition within the contract code. The code defines a contract global example containing 3 functions: getBlockInfo, getTXInfo, and getContractInfo. GetBlockInfo returns the current block number, the address of the miner who mined the latest block, and the hash of the previous block. GetTXInfo provides the sender's address of the current call, the amount of ether sent along with it, and the call's data payload. GetContractInfo returns the address of the contract and its ether balance. Each function showcases the use of Solidity's global variables such as block, MSG, and address this to access blockchain-specific info. Inheritance and contract composition. In Solidity, inheritance is a way to create a new contract that builds upon the features of an existing one. It enables code reuse and contract organization. In the given code, contract B inherits from contract A using the is keyword. Function foo from contract A is reused in contract B through inheritance. Contract B then defines an additional function bar, which internally calls foo. When bar is called, it returns the result of foo, demonstrating function reuse through inheritance. Interfaces and abstract contracts. In Solidity, interfaces define a contract's external functions without implementing them. They are similar to abstract contracts, but cannot have any functions with implementations. Interfaces cannot have state variables and can only inherit from other interfaces, not from classes. They are used to ensure certain contracts have specific functions that can be called externally. In the provided code, we have an interface named iCalculator that includes 2 function signatures for add and subtract. These functions, when implemented by a contract, will accept 2 arguments of type uint256 each and return a uint256. Given that this is an interface, there is no function logic present, just the declarations of what the functions look like. Library contracts and using for. In Solidity, libraries are special types of contracts that are designed to be reusable across other contracts. Similarly to base contracts, they are not deployed individually but included into the calling contract. The using for directive allows you to attach library functions to any data type within a contract. The provided code introduces a library named safemath, which contains a function add that safely adds two uint256 numbers, reverts if there's an overflow. Inside your contract, myContract, the using safemath for uint256 statement allows every uint256 variable to access the add method as if it were a native method to the uint256 type. Thus, value equals value.addAmount uses the library function to increment the contract's value safely. Constructors and contract creation. In Solidity, a constructor is a special function that is executed only once when a contract is created. It's often used for contract initialization, such as setting initial values of state variables or performing setup tasks. The code defines a Solidity contract named myContract with a single state variable owner. The constructor is marked with the constructor keyword, indicating it runs only when the contract is deployed. In the constructor body, owner is set to msg.sender, which refers to the address initiating the contract creation, typically the deployer of the contract. This setup ensures that owner is recorded at the time of contract deployment without the need to call any additional functions. Function overloading. In Solidity, function overloading refers to the ability to have multiple functions within a contract with the same name but different parameters. This allows for varied behavior while simplifying the interface, since the same function name can be used with different types or numbers of parameters. The provided code snippet defines two getValue functions with different signatures in the overloading example contract. The first accepts a single uint parameter and simply returns it. The second accepts a uint and a bool. If the bool is true, it adds 20 to the uint before returning it. When calling getValue, the Solidity compiler determines which function to invoke based on the provided arguments. Function overrides. In Solidity, function overriding is a feature that allows a function in a derived contract to have a different implementation than the one in its base contract. It's a critical concept for contract inheritance hierarchies and polymorphism. In this example, contract A defines a function foo that is marked with the virtual keyword, indicating that it can be overridden. Contract B, which inherits from A, overrides foo with its own implementation, signified by the override keyword. Calling foo on an instance of B will now return contract B, even if the call is via an interface of A. This is because B's foo function has overridden A's implementation. Custom modifiers. Custom modifiers in Solidity are useful for adding reusable precondition checks or effects to functions. They can make the functionality more modular, enhance readability, and reduce code duplication. The code defines a Solidity contract with a custom modifier only adults. This modifier takes an age parameter and checks if it is greater than or equal to the minimum age. The underscore acts as a placeholder for the body of the function that the modifier is applied to. The enter club function will only execute if this precondition is met, hence enforcing an age restriction on the function call. Import and use of external contracts and libraries. In Solidity, external contracts can be interacted with by importing their interfaces or contract code. Libraries, on the other hand, are special types of contracts that allow for the reuse of code. A library is not meant to be deployed by itself, but its functions can be called by other contracts. The code sample demonstrates how to import and use functionalities from an external contract and a library in Solidity. The import statements are used to include the code from some contract.sol and some library.sol. In myContract, we instantiate external contract with the address of a deployed some contract. The using statement allows us to attach library functions to a type, in this case uint. We call some function in external contract via use external contract function and apply a library function to a uint using use library function. Both external contracts and libraries enhance modularity and code reuse in Solidity development. Memory, storage, and call data. In Solidity, there are different locations where variables can be stored: storage, memory, and call data. Storage is a persistent state on the blockchain. Memory is a temporary place used to hold data during function execution, and call data is an immutable, temporary location used to store function arguments. The contract storage memory call data contains an array numbers which is stored in storage, indicating it will be persisted across function calls and transactions. Within the doSomething function, the inputs array received from the function call is located in call data, denoting that it's read-only and passed as function arguments. The temp numbers array is declared as a memory variable, which means it's a temporary space used in the function execution context, and it's modifiable. After calculations, temp numbers contents are assigned back to the storage variable numbers, updating the state on the blockchain. Data locations. In Solidity, data locations are important because they tell the compiler where to store variables. There are three main data locations: storage, memory, and call data. Storage refers to variables that are permanently stored on the blockchain. Memory is temporary and erased between external function calls. Call data is similar to memory but is read-only and contains function arguments. This Solidity code snippet includes an example of data locations. The storage array variable is defined in storage and persists between function calls. Call data array is read-only and passed as a function argument, suitable for external functions to avoid copying data and save gas. Memory array is defined in memory and only exists during the function execution. Within the example function, memory array is copied to storage array. A new storage reference new storage array points to storage array, allowing updates to storage directly. Attempting to modify call data array raises an error, enforcing its immutability. Hashing functions, kecac256, sha256, etc. In Solidity, hashing functions are used to securely convert data into a fixed-size hash. The most common hashing functions are kecac256, which is a version of SHA-3, and SHA-256, part of the SHA-2 family. These functions output a hash that makes it practically infeasible to derive the input from it, or to find two different inputs that produce the same output hash, collision resistance. Let's look at how to use these functions in Solidity. The code defines a contract hashing examples with two functions, hash using kecac256 and hash using 256. Each function takes a string as input and returns a bytes32 hash. The kecac256 function is more tightly integrated with Ethereum and often preferred for Ethereum-specific use cases. aby.encodePact is used in both to concatenate and encode the string into a bytes format that the hash functions accept. The produced hashes are deterministic. The same input will always yield the same hash output. Signatures and cryptography. Solidity provides built-in cryptographic functions. One of the most commonly used is kecac256, which computes the kecac256 SHA-3 hash of the input data. The function hashData takes a string input, encodes it using abi.encodePact, and returns the kecac256 hash. This is useful for creating a unique and fixed-size hash value from variable input data. Ether units and gas. On the Ethereum network, Ether is the native currency, but it can be denominated in various units. Ethereum provides several denominations that can make it easier to work with different quantities of Ether, especially given its high value per token. Solidity natively understands these units. The code declares three uint256 variables assigned with Ether, Wei, and Gwei units. Ether is the main denomination. Wei is the smallest unit, 1 Ether equals 10^18 Wei, and Gwei is commonly used for gas prices, 1 Ether equals 10^9 Gwei. Solidity automatically handles the conversion based on the unit name. Transactions and gas estimation. In Ethereum, transactions are the actions carried out by users to transfer Ether, interact with smart contracts, or deploy new contracts. These are formed as data packages that include information such as the nonce, gas price, gas limit, to address, value, and data. Transactions are uniquely identified by their hashes and require a signature with the sender's private key, ensuring security and ownership. Once submitted, They enter the transaction pool and await to be mined into blocks. The network confirms transactions through consensus, and once successful, the state of the Ethereum blockchain is updated. Blocks and time units. In Ethereum, a block is a collection of transactions, and each block is chained together with its predecessor through a cryptographic hash. Smart contracts can access block and time information to perform operations based on the current block number or timestamp. This can be crucial for certain logic, such as calculating time periods or ensuring actions happen after a certain block. Two global variables accessible in Solidity are block.number for the current block number and block.timestamp for the current block timestamp in seconds since the Unix epoch. The code defines a contract time-based contract with two functions. Update timestamp updates a state variable last updated with the current block timestamp. 1 minute has passed is a view function that checks whether at least 1 minute has elapsed since last updated was last modified. It utilizes the Solidity's time unit alias minutes for easy readability and calculation. When called, it compares the current block's timestamp with the sum of last updated and 60 seconds, 1 minute, returning true if the current time is greater or equal to this sum. ERC standards, ERC20, ERC721, ERC1155, etc. ERC stands for Ethereum Request for Comment, and these standards are guidelines for creating tokens on the Ethereum blockchain. Different ERCs cater to various use cases, such as fungible tokens, ERC20, non-fungible tokens, ERC21, and multi-token standard, ERC1155. Let's briefly overview these standards. ERC standards are integral to the Ethereum ecosystem, providing a framework for token implementation. ERC20 introduced a standard for fungible tokens, which are interchangeable and divisible. ERC721 introduced non-fungible tokens, NFTs, unique and non-interchangeable. ERC1155 is a newer multi-token standard that enables a single contract to manage multiple token types, both fungible and non-fungible, optimizing transactions and reducing the complexity of deploying a wide range of tokens. Interacting with contracts, call, delegate call, and static call. In Solidity, contracts can interact with each other using functions like call, delegate call, and static call. Call is a low-level interface for sending a message to a contract. Delegate call is similar but retains the context of the caller, and static call performs a read-only operation. The code defines two contracts: receiver, which can receive ether and data, and caller, which can interact with other contracts. The caller contract demonstrates the use of call to send data and ether to another contract, static call to perform a read-only operation, and delegate call to execute another contract's function within its own storage context. Each interaction is followed by emitting an event with the results. These functions provide the flexibility and tools required for contracts to communicate and leverage each other's code on the Ethereum blockchain. Oracles and data feeds. Smart contracts on Ethereum are isolated and cannot directly fetch data from external systems. Oracles are services that provide a bridge between the blockchain and the external world by feeding smart contracts with data from outside sources. Data feeds, on the other hand, are a type of oracle that specifically provides real-time data points, such as asset prices. Let's look at a basic example of how a smart contract might request data from an oracle. The given Solidity contract, price consumer v3, interfaces with the Chainlink Oracle network to fetch the latest asset price. First, it imports the aggregator v3 interface provided by Chainlink. The constructor initializes the contract with the address of a specific Chainlink data feed contract. The getLatestPrice function uses the latest round data method from this interface to fetch the latest round of price data and returns the price to the caller. Note that the other values returned by latest round data are omitted using blank identifiers and SA, because only the price is of interest in this function. Upgradable contracts. In the context of Ethereum and Solidity, upgradable contracts are a design that allows for the logic of deployed smart contracts to be changed without deploying an entirely new contract. Traditional smart contracts are immutable, but upgradable contracts use proxies and a separation of logic and data to allow developers to modify or fix contracts post-deployment. The The provided code snippet showcases a simple, upgradable contract architecture in Solidity using a proxy pattern. The logic contract holds the actual contract logic, such as a counter state variable and a function to increment it. The proxy contract holds the address of the current logic contract and uses a fallback function to delegate calls to it. When a user interacts with the proxy contract, it will implicitly forward the interaction to the active logic contract. If there's a need to upgrade, the address of the logic contract can be changed in the proxy without altering the logic that interacts with the state. This pattern is vital for creating flexible and maintainable systems on the blockchain, where immutability of deployed code is a default constraint. Ethereum Name Service, ENS. The Ethereum Name Service, ENS, is a distributed, open, and extensible naming system based on the Ethereum blockchain. ENS's job is to map human-readable names like alice.eth to machine-readable identifiers such as Ethereum addresses, other cryptocurrency addresses, content hashes, and metadata. ENS also supports reverse resolution, making it possible to associate metadata such as canonical names or interface descriptions with Ethereum addresses. ENS functions similarly to the Internet's domain name system, DNS, but with the security properties of the Ethereum blockchain. The primary components of ENS are the registry, resolvers, and registrars. The registry maintains a list of all domains and subdomains. The resolvers translate the names to addresses, and the registrars are responsible for domain allocation. ENS integration allows users to send transactions to human-readable addresses, enhancing the user experience by avoiding the need to handle long hexadecimal addresses. Payment channels. Payment channels on Ethereum allow for off-chain transactions that can be settled on-chain after multiple transactions. This helps in reducing fees and congestion on the Ethereum network. Let's consider a simple payment channel between two parties, Alice and Bob. They can transact multiple times off-chain, and when they are ready to settle, they use the smart contract to distribute the funds based on the last signed state of the channel. In this Solidity code, we define a simple payment channel contract. It is initialized with the addresses of the sender, the intended recipient, and a duration for the channel's expiration. The close function allows the recipient to close the channel by presenting a signed message, signature, with the agreed amount. The isValidSignature function, not fully implemented here, should check that the signature is indeed from the sender and matches the amount. If the signature is valid, the recipient can transfer the agreed amount. The sender has the ability to extend the expiration time if needed, and the claim timeout function allows the sender to reclaim their funds if the expiration time has passed. Common attacks: reentrancy, overflow, underflow, front-running, etc. Reentrancy is an exploitative attack that can occur when a smart contract function makes an external call to another untrusted contract, and that external contract makes recursive calls back to the original function. The code above is a simple smart contract that allows deposits and withdrawals of Ether. In the withdraw function, Ether is sent out to the user before the user's balance is set to 0. This ordering creates a vulnerability, as an attacker can create a malicious contract that overrides the fallback function to recursively call withdraw before the user balance is updated. Security patterns: checks, effects, interactions, rate limiting, etc. The checks, effects, interactions pattern is a security pattern used to reduce the risk of reentrancy attacks. It advises to perform all the checks, validations first, then make the necessary state changes, effects, and only after that to interact with other contracts. The provided code illustrates the checks, effects, interactions pattern. The withdraw function first performs a check to ensure the user has sufficient funds. Require balances the sender score amount. It then updates the state by deducting the amount from the sender's balance. Balances the sender scores amount. Only after these effects have been accounted for, it interacts with another contract address by sending Ether, msg_sender.call value or amount. This helps prevent reentrancy attacks, because even if a malicious contract were to call back into withdraw, it would fail at the check due to the updated state. Security tools and auditing: Mithril, Slither, etc. Mithril Classic is a security analysis tool for Ethereum smart contracts. It helps developers to detect a variety of security vulnerabilities using concolic analysis, taint analysis, and control flow checking. Let's consider an example of how Mithril can be used to analyze a simple smart contract for potential security issues. In the provided code, there is a simple Ethereum smart contract named vulnerable contract, which includes common functions like deposit and withdraw. The contract potentially suffers from a re-entrancy attack because the state is updated after sending Ether, which is a well-known vulnerability. When Mithril analyzes this code, it will flag the withdraw function, indicating that it might be vulnerable to a re-entrancy attack, leading to potential theft of funds if not mitigated properly. Mithril would generate a report detailing the vulnerability, allowing developers to take preemptive action to secure their contract. Using modifiers for security checks. Modifiers in Solidity are code snippets that can be run before and/or after function calls in contracts. They are used to manage permissions and validate requirements. Security can be enhanced by using modifiers to ensure that certain conditions are met before a function can proceed to execution. This guards against unauthorized access and invalid data. The code snippet defines a modifier only owner that restricts the execution of functions to the owner of the contract only. It does this by checking msg.sender, which refers to the sender of the current call, against the owner state variable. The require statement ensures that the condition msg.sender equal owner is true. If not, it reverts the transaction with the message, not the owner. The underscore represents the body of the function the modifier is applied to. The function secure function uses only owner modifier, thus can only be executed by the address that deployed the contract, i.e. the owner. Contract lifecycle management. Contract lifecycle management involves practices that ensure a smart contract remains secure throughout its entire lifecycle, from development to deployment to eventual decommissioning. This involves careful planning for upgrades, maintenance, and migrations, as well as mechanisms for pausing or destroying a contract when necessary. The code snippet includes mechanisms for pausing operations and for self-destructing the contract. The paused state variable can be toggled using the pause and unpause functions, controlling the execution of operations within the contract. Meanwhile, the emergency withdraw function makes use of self-destruct, which is used to remove the contract from the blockchain and send its remaining Ether to the owner, effectively ending the contract's lifecycle. Testing and debugging. Unit testing is crucial in smart contract development to ensure each function behaves as expected. Truffle is one of the most popular frameworks for Ethereum development that provides a testing suite to write automated tests in JavaScript or Solidity. The code represents a basic Truffle unit test for a fictional My contract. It checks whether My function returns true. Tests are written within contract blocks that provide a cleanroom environment with fresh deployed contracts. The eat function defines a test case where assert.equal is used for assertions comparing the returned value to true. Error messages are given as the final argument to assert functions to provide better feedback if tests fail. Bug bounties and responsible disclosure. Bug bounties in the context of Solidity and smart contracts are programs offered by many websites, organizations, and software developers, by which individuals can receive recognition and compensation for reporting bugs, especially those pertaining to security vulnerabilities and exploits. The example smart contract bug bounty includes a function report bug for users to report bugs they find. When a user reports a bug, an event bug reported is emitted, which logs the address of the reporter and the bug description. This simple contract serves as a foundation for implementing a bug bounty system on the blockchain. However, a real-world implementation would include additional features such as verification of the bug, the decision process for bounty payouts, and measures to prevent abuse of the bug reporting system. Solidity unit testing frameworks, Truffle tests, hard hat tests. Truffle is a popular development framework for Ethereum that includes a suite of testing tools for smart contract development. To write Truffle tests, you can use JavaScript or Solidity. Here's a simple example of a Truffle test written in JavaScript that tests a smart contract method for setting and retrieving a value. The code imports the contract using artifacts.require, hooks into the Mocha testing framework provided by Truffle using the contract function, and then sets up a before each block to deploy the contract before each test. Inside the it function, it performs the test by calling the set method of the contract, then retrieves the value using the get method, and finally uses assert from chai to check if the value was properly set. Writing test cases and test suites. Test cases and test suites are crucial for ensuring that smart contracts behave as expected. In Solidity, you can write tests using the JavaScript testing framework Truffle, which works with the Mocha testing framework and chai assertion library. A test suite is a collection of tests that are executed together. Each test case is an individual unit of code designed to check the correctness of a particular function or feature of the smart contract. The provided code demonstrates how to write a test suite in Solidity using Truffle. Here, my contract is the smart contract being tested. 2 test cases are wrapped in a contract block that ensures each test runs against a fresh instance of the smart contract. The first test checks if the contract initializes with the correct value. It retrieves the deployed instance, calls the getStoredValue function, and uses assert.equal to check the value. The second test verifies that the value updates correctly when setStoredValue is called, confirming the contract reacts as expected to state changes. This pattern of writing assertions ensures that contracts function as intended under different conditions. Deployment scripts. Deployment scripts are crucial in automating the process of deploying your Solidity smart contracts to a blockchain. These scripts interact with the network and handle the deployment of your compiled contract code. Often, deployment scripts will also involve some initial configuration of the deployed contracts. In the provided code, we are using a deployment script that is typically used within the Truffle framework, which is a popular development framework for Ethereum. The script starts by requiring the contract artifact, which includes the compiled contract code and its ABI. The artifacts.require method is specific to Truffle and loads the contract's information. The module.exports is a JavaScript exporting module pattern. Inside, we define a function that takes the deployer object as an argument. The deployer.deploy function is called to deploy my contract to the blockchain. This function automates the deployment task when running migration commands using Truffle. Mainnet and testnet deployment. In Solidity development, before deploying a contract to the Ethereum mainnet, it's crucial to test the contract thoroughly to ensure it works correctly and is secure. This is where Ethereum testnets come into play. Testnets simulate the Ethereum environment, allowing developers to deploy and interact with contracts without spending real Ether. Once the contract is fully tested, it can be deployed to the mainnet, which involves real Ether and live transactions. The provided code is a simple Solidity smart contract that includes a state variable value and a function to set that value. To deploy this contract to a testnet or the mainnet, you'd typically use an Ethereum wallet such as MetaMask and a deployment script, often written with the help of a framework like Truffle or Hardhat. Deploying to testnets like Rinkeby or Ropsten helps to test the contract's functionalities in an environment similar to the mainnet without the risk of losing real assets. Contract verification on Etherscan. After deploying a smart contract to a blockchain network such as Ethereum, you might want to verify the contract's source code on Etherscan. Verification makes the code publicly viewable and transparent, allowing users to interact with the contract more trustfully. Here's a step-by-step explanation of the process. Verification on Etherscan is not a code-based process, but rather a series of steps on the Etherscan website. 1. Go to the contract address on Etherscan. 2. Click on the Contract tab, then select Verify and Publish. 3. Fill in the details such as compiler version, optimization settings, and enter the Solidity contract code. 4. If your contract uses constructor arguments or imports from other files, you'll need to provide the constructor arguments in A-encoded format and also verify each imported contract if not already verified. 5. Etherscan compiles the code you provided with the same settings and matches it against the bytecode on the blockchain. 6. Upon successful verification, The Contract Source Code tab will be available to the public, displaying the readable Solidity code. Using JavaScript TypeScript with Solidity. To interact with Solidity smart contracts from JavaScript TypeScript code, we employ web3.js or ethers.js libraries. They allow us to communicate with the Ethereum network, deploy contracts, and invoke their methods. Here's a basic example of deploying and interacting with a Solidity contract using JavaScript and the ethers.js library. This code snippet demonstrates how to connect to Ethereum using ethers.js by setting up the provider and signer. We then instantiate a contract object with its address and ABI, which lets us interact with the contract. The sum function call is an example of executing a contract's method, and we await the transaction's confirmation on the network. Integration with frontend Web3.js, ethers.js. Once you have a Solidity smart contract written and tested, the next step is to make it accessible to users through a front-end application. This can be a website or a mobile app. To interact with the Ethereum blockchain from your front-end, libraries like Web3.js and ethers.js are used. They provide an abstraction over the Ethereum JSON RPC API, simplifying the process of sending transactions, querying contract states, and listening for events. The code snippet is a JavaScript function that utilizes ethers.js to fetch the balance of an Ethereum address. First, it creates a provider, which is an abstraction for the connection to the Ethereum network, pointing to the user's own Web3 provider, typically injected by a browser extension like MetaMask. Then, it uses the getBalance method provided by the provider to retrieve the balance of a specific address. It logs out the balance converted from WAY to ETH using the format ether utility function. Gas optimization techniques. When declaring variables in Solidity, using types that require less storage can save gas. This is because the EVM operates on 32-byte word boundaries. Although uint256 is the most commonly used integer due to its large size, if you know your variable will not exceed a certain range, you can choose a smaller data type, like uint8, which can cost less gas since it uses less storage. Efficient use of storage. In Ethereum, the storage is a costly resource. The EVM, Ethereum Virtual Machine, charges gas for storing and modifying data. Thus, it's crucial to use storage efficiently to minimize transaction costs. The above Solidity code presents a struct with two uint128 variables instead of uint256. Since the EVM operates on 256-bit word boundaries, it can pack these two uint128 variables into a single storage slot. This reduces the amount of storage needed and minimizes costs. The function set allows updating the values in a single transaction, further optimizing the use of storage. Remember that tightly packed variables can only occur if they are in a struct or if they are declared adjacently in a contract. Coding Standards Solidity Style Guide. Proper naming conventions enhance code readability and maintainability. This includes using camel case for variables and functions, and Pascal case for contract and struct names. The contract name bank account uses Pascal case, which clearly signifies it's a contract. The variable account balance uses camel case, indicating it's a variable. The function deposit funds follows the same camel case convention, showing it's a function. Documentation, NatSpec. NatSpec, short for Natural Specification, is a methodology for documenting Solidity code. It involves writing comments that explain the function and purpose of the code, which are then processed by tools like the Solidity compiler. These comments can greatly improve code readability and maintainability, especially when collaborating with others or when reviewing code after a period of time. In the provided code excerpt, NatSpec comments are used to document a Solidity smart contract and its functions. The tags @title, @author, @notice, @dev provide metadata about the contract, its purposes, and its development details. Function-level comments describe what each function does, with @param explaining function parameters and @return for return values. This form of documentation is crucial for understanding the intended use and behavior of smart contract functions. Code reuse and modularity. In Solidity, code reuse and modularity are critical for creating efficient and maintainable smart contracts. By using inheritance, interfaces, and libraries, developers can write modular code that can be easily reused and updated. The provided code demonstrates modularity through the use of a library called SafeMath. This library ensures safe arithmetic operations, which protects against overflow issues. By using the add function from SafeMath, the token contract can safely increment the user's balance. This exemplifies code reuse, as the same SafeMath library can be used across multiple contracts to handle arithmetic safely. Audit checklists. Audit checklists are crucial for ensuring that smart contracts are secure, efficient, and reliable. They consist of a series of items that developers and auditors check against to avoid common pitfalls and ensure best practices in Solidity programming. While no code is directly associated with an audit checklist, it is a conceptual tool used before deployment and during reviews of smart contracts. A checklist may include items such as checking for overflow, underflow vulnerabilities, proper visibility of functions and state variables, adherence to naming conventions, gas optimization practices, use of up-to-date and secure Solidity versions, and comprehensive testing for all contract functionalities. Continuous integration and delivery for smart contracts. Continuous integration, CI, and continuous delivery, CD, are practices aimed at improving the quality of software and its development process. For smart contracts, especially due to their immutable nature once deployed on a blockchain, it's crucial to automate testing and deployment stages to avoid costly errors. While specific CI/CD tools or platforms may vary, the key idea is to set up a system that automatically runs tests and security checks on your smart contracts whenever changes are made. This typically involves using a testing framework such as Truffle or Hardhat and integrating with a CI/CD service like GitHub Actions or Travis CI. The CI pipeline runs unit tests, linter checks, and security audits on every push or pull request, ensuring that only thoroughly tested code gets merged into the main branch. The CD pipeline can automate deployment to test networks and prepare for production deployments, minimizing human error. Behavioral patterns, state, strategy, template method. The state pattern is a behavioral design pattern that allows an object to alter its behavior when its internal state changes. In Solidity, this pattern is useful to manage the stages of a contract, such as in a workflow or a state machine. In this code, the auction contract illustrates the state pattern where the auction can be in different states. An enum type is used to represent the possible states of the auction. The contract includes functions to transition the auction state, such as starting, ending, and cancelling. The bid function checks the current state before proceeding, enforcing the behavior corresponding to the running state. Thus, the contract's behavior is governed by its state, demonstrating the state pattern. Security patterns, guard check, pullover push, emergency stop. The guard check pattern helps prevent unauthorized access or invalid states in functions. This is typically implemented using modifiers that assert certain conditions. In the code, there is a modifier named onlyOwner that checks whether the msg.sender is the current owner before allowing changes. The modifier is used in the changeOwner function to ensure that only the owner can change its state. Lifecycle patterns, mortal, factory. The mortal pattern refers to a concept in which smart contracts are designed to have a self-destruct mechanism. This allows the owner of the contract to destroy it and remove it from the blockchain, a useful feature for contracts lifecycle management or for removing contracts that are no longer needed. In the provided mortal contract, the constructor sets the creator of the contract as its owner. The destroy function allows only the owner to destruct the contract using self-destruct, which removes the contract from the blockchain and sends any remaining ether to the owner's address. This pattern gives control over the contract's lifecycle to its owner. Financial patterns, revenue share, withdrawal from contracts. In a revenue share pattern, the contract divides incoming funds among predefined addresses proportionally to their share percentage. This pattern ensures automatic and trustless distribution of funds, which can be beneficial for partnerships or collaborative endeavors where profits need to be shared. The revenue share contract takes an array of stakeholders and their respective share percentages upon deployment. When the contract receives ether, the distribute function is called to transfer a portion of ether to each stakeholder. The amount is calculated based on their share percentage. It's important to ensure the total percentages sum up to 100, and a proper safeguard against over or under distribution is through using safe math operations. EVM internals, stack, memory, storage, opcode. The Ethereum Virtual Machine, EVM, is the execution environment for smart contracts in Ethereum. Understanding its internals is key to writing efficient smart contracts. The EVM has its own runtime stack, memory, and storage, which are used during the execution of smart contract code. Opcodes are low-level instructions that define the set of operations that can be performed by the EVM. The EVM stack is a last-in, first-out (LIFO) structure with a maximum size of 1024 elements, used for evaluating expressions and storing temporary variables. Memory is a byte-addressable space that a contract can use during execution, and it's volatile, meaning it's erased between transactions. Storage is a key-value store where each contract's persistent state is kept. This is non-volatile and remains between transactions. Opcodes are the basic instructions, like add, multiply, etc., that the EVM can execute during the processing of bytecode. Consensus mechanisms, POS. Consensus mechanisms are protocols that ensure all nodes in a blockchain network agree on the shared ledger's state. Proof of work, POW, and proof of stake, POS, are two predominant mechanisms. POW requires miners to solve complex cryptographic puzzles to validate transactions and create new blocks. POS, on the other hand, allows validators to create new blocks based on the number of coins they hold and are willing to stake, as collateral for the chance to validate transactions. Consensus mechanisms are fundamental to maintaining the integrity and security of a blockchain. In POW, miners compete to solve puzzles, and the first to solve it gets to add a new block to the blockchain and is rewarded. This process is energy-intensive. In POS, validators are chosen to create new blocks based on their stake in the network, making it a more energy-efficient alternative. POS also introduces different concepts like forging or minting instead of mining, where instead of competing using computational power, validators are chosen semi-randomly. Layer 2 solutions, rollups, state channels, sidechains. Rollups are solutions that execute transactions outside the main Ethereum chain, Layer 1, but post transaction data on it. They aim to scale the network by handling more transactions per second and reducing fees. Rollups come in two flavors, optimistic rollups and ZK rollups. Here's a conceptual illustration rather than executable code, showcasing how a rollup might batch transactions and submit them to the main chain. This is a simplified example representing the interaction of a rollup contract with Layer 1, where transactions are batched and processed off-chain. For an optimistic rollup, submissions assume transactions are valid by default and can be challenged within a dispute window. ZK rollups use cryptographic proofs, zero-knowledge proofs, to attest to the validity of transactions without revealing data about them. Interoperability, Cosmos, Polkadot. Interoperability refers to the capability of different blockchain networks to communicate, share data, and conduct transactions with one another. This is important for creating scalable and interconnected blockchain ecosystems. Two notable projects that focus on this are Cosmos and Polkadot. They use different architectures to enable blockchains to interoperate. Cosmos utilizes a hub-and-spoke model, connecting various blockchains, zones, through the Cosmos hub, which maintains the network's state and facilitates transactions between zones. Polkadot uses a relay chain where various blockchains, parachains, are attached. The relay chain enables security sharing and inter-parachain communication. Both systems employ consensus mechanisms and layers to facilitate cross-chain interoperability, but they don't entail Solidity code examples, as the interoperability is achieved at the infrastructure level rather than the smart contract level. Smart contract upgrades, proxy patterns, diamond standard. In the context of Ethereum, smart contracts are immutable once deployed to the blockchain. However, developers often require the ability to upgrade contracts to fix bugs, improve functionality, or add features. Proxy patterns offer a solution to achieve upgradability by separating the contract logic from the data storage. We will look at the two main proxy patterns, the transparent proxy pattern and the universal upgradable proxy standard, UUPS. This code snippet demonstrates how to deploy a transparent proxy using the OpenZeppelin library. The deploy transparent proxy contract is created with logic, address of the logic contract, and admin, address with privileges to upgrade the contract. The deploy proxy function creates a new instance of transparent upgradable proxy, passing the logic contract's address, the admin's address, and constructor arguments for the logic contract. The proxy delegates calls to the logic contract and can be upgraded by the admin. Gas tokens and gas saver techniques. Gas tokens take advantage of the storage refund mechanism in Ethereum, which allows smart contracts to receive a refund for freeing up storage space. To save on gas costs, these tokens can be minted when gas prices are low and redeemed to offset gas costs when prices are high. This concept hinges on two main operations: minting, allocating storage, and freeing, deleting storage, each operation being a smart contract function. The provided code defines a simple gas token smart contract. The mint function allows a user to mint gas tokens by creating and sending zero-value transactions to unique addresses generated deterministically from their own address. This operation consumes gas and fills Ethereum's storage. The free function allows users to claim a gas refund by freeing the storage through a call to those same addresses. Refunds are given for freeing storage as an incentive to clean up the blockchain. This code is conceptual and simplified. Real gas tokens involve more complex mechanisms for optimal gas savings. Ethereum Improvement Proposals, EIPs. Ethereum Improvement Proposals, EIPs, are design documents providing information to the Ethereum community or describing a new feature for Ethereum or its processes or environment. The EIP should provide a concise technical specification of the feature and a rationale for the feature. EIPs do not generally include actual code. Instead, they are a design specification that describes a proposed change to the system. EIPs are an important part of Ethereum's governance and include various types such as standards track EIPs, e.g. ERC20, which propose changes that affect most or all Ethereum implementations, informational EIPs, which design guidelines or supporting information, and meta-EIPs, which propose changes to the EIP process itself. Authors submit EIPs as a document, which is then discussed and reviewed by the community before it can be adopted. Full-stack DApp architecture. A full-stack decentralized application, DApp architecture, encompasses both the front-end interface and back-end smart contract logic. The front-end is built typically using web technologies and communicates with the blockchain via a Web3 provider. The back-end consists of smart contracts that run on the Ethereum Virtual Machine, EVM. These contracts govern the rules, execute logic, and manage the decentralized state of the application. The presented Solidity code defines a simple smart contract named Simple Storage, which has a state variable data. There are two functions, setData and getData, that allow users to update and retrieve the value of data respectively. Such a smart contract would be a basic back-end deployment on the blockchain in a full-stack DApp, managing state in a decentralized manner. Integrating with IPFS for decentralized storage. To integrate IPFS, Interplanetary File System, with a Solidity project, you typically handle the IPFS part off-chain because Solidity is designed to work with smart contracts on the Ethereum blockchain, which are not suited to directly handle large amounts of data due to gas cost. Files are uploaded to IPFS through an off-chain process, and the resulting IPFS hash is stored on-chain within a smart contract. Here's an example of how a typical integration might look. The code defines a simple Solidity smart contract which maps Ethereum addresses to IPFS hashes. The setIPFS hash function allows users to associate their Ethereum address with an IPFS hash, typically after they've uploaded a file to IPFS through a client-side application. The getIPFS hash function allows anyone to retrieve the IPFS hash associated with a particular address. The IPFS content itself needs to be uploaded and retrieved using an IPFS client, and the hashes are simply references that are stored on the Ethereum blockchain. Front-end interactions with MetaMask. To interact with blockchain through a web interface, MetaMask can be used as an Ethereum wallet and browser extension that allows users to run Ethereum DApps without running a full Ethereum node. It's commonly adopted by web applications to integrate Ethereum blockchain functionality. The provided code snippet is a function named connectWallet that attempts to connect to the user's MetaMask wallet. It first checks if the window.ethereum object exists to confirm MetaMask's presence. If it does, it uses window.ethereum.request with the method eth_request_accounts to ask the user's permission to access their Ethereum accounts. If the user grants permission, their account addresses are returned and logged to the console. Otherwise, an error is logged. If MetaMask is not installed, a message prompts the user to install it. Using the Graph protocol for indexing and querying. The Graph is a decentralized protocol for indexing and querying data from blockchains. It allows developers to efficiently and quickly obtain the data they need through GraphQL without running a full node. This helps in building more performant and complex decentralized applications, DApps. Typically, one must define a subgraph manifest, which specifies the smart contracts of interest, the events within them to watch, and how data should be mapped to the GraphQL entities. This happens in the subgraph.yaml file. GraphQL schemas are defined to determine how the data can be queried. These define the entities and fields that will be stored in the graph. When events are triggered from the blockchain, the graph's nodes, called indexers, pass the events and store the specified data, which any application can query using GraphQL.